cases, in some substances, there will be a time in between the solid state and the liquid state where these molecules in the substance cannot translate around. They cannot move vertically, horizontally, or in that sense. However, they are free enough that they can rotate. And since the bonds that kept them from rotating have just been weakened, generally all the molecules within the liquid crystal will have the same orientation. Now, this anisotropic factor is the most notable aspect of liquid crystals, which make its optical properties. There are three types of liquid crystals. There's the mimetic phase, the smectic phase, or the smectic A and the smectic C phase. So in the nematic phase, this is the last phase before liquid. This is where all the molecules in the substance still have the same orientation. However, in every other sense, their position, everything is unorganized. So if you imagine it like a bunch of needles lying on the ground attracted to a magnet. The smectic phases, A and C, in both of them, this occurs closer to the solid phase than the liquid phase. And here what happens is that the general structure, as you can see here, is still maintained. So there is a sense of periodicity. In the specific type of smectic A liquid crystals, there are layers being formed. So just as, what was it? It was graphite or graphene? Which one's the one with the layers? Doesn't matter. But anyways, there's graphene, layers that... Graphene, yeah, I think so. That can move over each other.
Hang on, graphene is one layer, graphite is multiple layers. Sorry, I was muted.
And he asked the one with one layer.
Yeah, graphite. So as you can see here, there's a periodicity in the layers. Now the smectic C phase is very similar to this. However, the difference is that instead of a common orientation that is close to the alignment of the plane, so in here case, if this is the plane, can I annotate? Yeah. So if this is the plane, the orientation is perpendicular. In the smectic C phase, this is where this orientation is very much angled. So it would be when the molecules are facing in that direction, something like that. Now, how do I get rid of this annotation? There you go. The progression occurs as follows. So you go from solid, like here, to the smectic C phase. So somewhat like this, then to smectic A, a little bit less organized, and then the nematic phase, and then liquid. Liquid crystals are only formed when a substance meets two criteria specifically. A, the substance has to be has to be oblong in shape. That's why they are drawn in this way, and this allows for the this allows for these orientation and translation factors, so that rotation can't just freely happen. And generally, liquid crystals are formed from organic compounds because of the bonding throughout them. Now, the characteristics of liquid crystals. So liquid crystals are very viscous, however, they do not commonly flow. As such, they are classified as non-Newtonian fluids. Liquid crystals can interact with light or all polarizations regardless of their highly oriented molecular structure. Now, this, of course, depends on which liquid crystal you're talking about. This is because of the organized manner of the orientation and the structure of the liquid crystals. So if you imagine kind of like the liquid crystals, when they're similarly oriented, create somewhat of a diffraction grid, in a sense, that interacts with lights. It doesn't interact in the same way, but essentially it's the same. Now, the applications of liquid crystals are really interesting. So the most common application, as everybody knows, is in liquid crystal displays. The way that this works is that you take a set of nematic liquid crystals, so ones that very easily rotate and ones that aren't periodic in the structure, and you allow the crystals to reorient themselves with a very weak magnetic or electric field. And using this by reorienting the crystals, since the crystals are anisotropic, this means you're also changing the optical characteristics of this of the crystals. So by reorienting them when they're in the nematic phase, you can create something which is akin to a optic switch. Now, when specifically talking about liquid crystal displays, there's another piece of chemistry that is used, and that is the chirality. A compound is defined as being chiral if no translation or transformation is able to superimpose an image of that compound onto any mirror image of that compound on any axis. So essentially, any way you move it, you cannot superimpose it. You cannot lay it on top of each other. In this case, in this specific example of this compound, which does form a liquid crystal, the asterisk here indicates where the chirality occurs. So any superposition or rotation of the rest of this would allow for the superposition to occur. However, due to this specific component, this is not possible. So let me just see what I want to talk about next. Yeah. Let me just skip over some of the more boring parts. Now, notice in this compound the consistency of the planar bonds. So while many of the hydrogens do branch off as a whole, the bonds with the intramolecular bonds in this compound are planar, which allows it to create this elongated shape. Furthermore, due to its high molecular mass, this compound experiences very strong London dispersion forces. And whilst this compound is generally not polar, the drastic imbalance of mass along the parallel axis, this axis here, allows the compound to undergo the liquid crystal state, as the London dispersion forces are stronger on one side than on the other, which means that some ends are quasi-attracted to other ends, creating the common orientation within the compound and the crystalline nature of the solid state of this compound. As the compound heats and melts, it becomes more and more free to move. However, as it does not form a common lattice, as we can see with magnesium dioxide, silicon dioxide, yeah, that's the one. Silicon dioxide. The transition between the solid and liquid phase is very subtle and very slow, and thus free movement with common orientation occurs quite easily. So this is one of the compounds that is commonly found in liquid crystal displays. Now, another really interesting and unknown application of liquid crystals is in the soap industry. Now, the compounds in soap can commonly form a type of liquid crystal in the smectic phase, which is different to the liquid crystals formed in the nematic phase. And this is a different form of smectic phase, not smectic A or smectic C. In this case, liquid crystal that is formed is called a lamellar, which is, I wasn't able to find out too much about, but which essentially means is the polymer equivalent of smectic layering. So if you imagine the layers that I demonstrated before in the, I should go back. Imagine the layering, and if you imagine those layers create somewhat of a polymer in that sense. It's like a quasi-polymer. It's not really a polymer, but it has polymer characteristics. That is what the lamellar phase is. And so because the soap molecules are elongated and contain a hydrophilic head and a hydrophobic tail, when one end bonds with water and the other end bonds with oils, because the soap is a liquid crystal, the orientation is maintained. So you can say that one end of the soap will always want to gather oils, and the other end will always want to stick with water, meaning that this really increases the efficiency and the ease in which soap removes oils from water, as the compounds in the soap don't actually need to reorient themselves in order to bond with the oils. The last thing I'm going to talk about, is the economic factor. So the liquid crystals are natural byproducts. So They were discovered in I think it was the 1920s by an Austrian scientist, of course. But since they can be formed very easily in nature just by using the correct compounds and making sure the correct heating and cooling pattern is maintained, this makes them very, very cheap to produce, and especially in the application of liquid crystal displays, it makes them vastly more utile. Furthermore, another economic factor is that many industries for many industries, the application of liquid crystal displays, again specifically, is a lot safer, because whilst the liquid crystals, with their optical characteristics, interact with polarized light, as well of any nature, this means that the light that escapes a liquid crystal display is not polarized. So that means that even if you're wearing sunglasses, for example, as a pilot, you can still see what is on the screen as the light is not polarized. Yeah, I think pretty much it on my part.
Very good.
Sorry, it was a bit boring now.
Right, it was good. It was very good. I liked